Hello, this is Mr. Harris with the video for pages 21 through 23 for the classwork posted for the polynomials unit. Remember, the link with the intro to polynomials unit has the original document. Again, this is pages 21 through 23. There will be a quiz posted. Expect 2 more videos. Then I will post the study guide and expect a quiz sometime next week. Okay, so here's number 1. Linear containing this coordinate. Let me go ahead and label this x comma y with 4 as a 0. I'm going to go ahead and write this as a coordinate. 4 as a 0. When they say 0, remember 0, roots, solutions, all the same thing. Also x-intercepts. They're all one and the same thing. The x-intercept is where is it on the x-axis when y is 0. So we also have the coordinate 4 comma 0, and that's what that coordinate is. This is another x, another y. Let me go ahead and label this x sub 1, y sub 1, x sub 2, y sub 2. Because you know it's linear, we're going to have to figure out the slope. M equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Let's go ahead and figure out the slope. 0 minus -5 divided by 4 minus 2 equals 5 divided by 2. 5 halves, that there is the slope. Then I'm going to my point slope form of an equation. Look at all these equations we know for linear functions, straight lines. Y sub 1 minus y equals m times x sub 1 minus x. Actually, the good thing is, technically, I need to switch this up because I always remember when I multiply, I get the slope times x, and then I get a number. So it's these little things that help us remember what stays a variable x and what do we plug a number in for. All those little things randomly in college, it might be 2 years till you see this again. Little things like that help you remember. When I distribute based off of this formula, which we all know so well, slope times x. Well, to have slope times x, I have to leave x as x. I can't plug a number in. Let me go ahead and choose this because it's simple, 4 comma 0. So I have y minus 0 equals my slope 5 halves times x minus 4. Getting rid of that 0, y equals 5 halves times x minus 4. This is certainly a valid equation. If I want to simplify it further, I can write it as y equals 5 times x divided by 2 minus 5 times 4 is 20. 20 divided by 2 is 10. This is also a valid equation. There you go. Again, for those of you taking calculus, the derivative is the slope of the tangent line to the curve. So believe it or not, you will be using linear equations in calculus on some level. I suggest you practice this on your own. Linear with -10 as a 0 and 8 as a y-intercept. I've done that already, you'll be okay. This would be the x-intercept, that would be the y-intercept. Again, the solutions will be posted as a PDF with this video in the Google Classroom page. 6 says it's only 0. I'm going to do 4 for you, and I'll leave you to do 3 on your own. Contains this point, and it has 2 zeros, but we know quadratic equations always have 2 zeros, so there's nothing to that. But I'm going to do this because this is 6 is its only 0, but because quadratic equations are squared, hence the degree is 2, this has to be a root of multiplicity 2. Multiplicity 2. Because it has to have 2 solutions, even if that solution is multiplicity 2. If we look at our parent function, y equals x squared, the root here is 0 of multiplicity 2 because it's a bounce point. It hits the x-axis and then it bounces up. That's what multiplicity 2 looks like. whatever linear equations, whatever the linear equation is, this is of multiplicity 1. 1 root of multiplicity 1 because it's a pass-through point. Remember, odd is pass through. For those of you that maybe didn't watch the last video. And even powers are bounce points. Again, if I'm talking too slow in videos, YouTube, you can change the speed. Watch me at 1.5 or two times as fast. Save yourself and help yourself out. Such is life. This is your life to live, not mine. So let's jump and do 4, right? Yeah. Quadratic containing this coordinate. So let's think about how we're going to do this. Typically, we've done things with 2 roots, but this is different. I'm going to set this up. I'm going to ignore this for the time being and try to solve this. Y equals 6 is a root, so we have x equals 6. So working backward, the factor is x minus 6 equals 0. So we have y equals x minus 6 squared. So we literally took the parent function and we moved it to the right 6 units. And this is what the graph looks like, jumping over 6 units. Now, this is that ace up the sleeve method if you saw my intro to polynomials video. The ace up your sleeve. A lot of people, for some reason, they'll use a capital A. I don't know why it looks nice, ace up your sleeve. Other sources use lowercase a. It really don't matter, people. It really don't matter. Let me use a capital A. Why not, right? Okay. This is how we're going to make sure or force it through this coordinate. If you notice, I have an x, I have a y. So I'm going to plug -4 in for this x. I'm going to plug 3 in for this y. I'm going to solve for a. And whatever a is, that's what's going to guarantee it. That's what's going to stretch it or compress it, however it is, to make sure it goes through that coordinate. The ace up your sleeve method. So let's look at this. I have, I'm actually going to do this on another piece of paper so I don't run out of space. So I have my y is 3 equals, okay, a times -4. Remember when you substitute, plug it in using parentheses, minus 6 squared. I'm sorry, I'm glad I caught that. Sometimes my brain jumps. Obviously, we know it's not raised to the 6th power because it's a quadratic. Let me change the 6 to a 2. You should have gotten that easy though. Okay, so let's simplify it. 3 equals a times -4 minus 6, that's -10 squared. So the next step, we have 3. I'm focusing it. I don't know why it's not wanting to focus. Okay, 3 equals a times 100, -10 squared. So a is 3 divided by 100. 3 divided by 100 is a perfectly valid number. So my equation is y equals 3 divided by 100 times x minus 6 squared. And that's my quadratic equation. Let's go to Desmos graphing calculator to verify this. Okay, so let's type in y equals 3 divided by 100, x minus 6 squared. And let's look for that coordinate, -4, 3. There we go. Yeah. Unless it's a root, it doesn't let me sort of hold it. Here we go. Almost. Technically, it would have to be exactly spot on, and I got it once. There we go. -3, 4, or -4, 3. The x is -4. Let's play with this. Let's change this 100 to 10. Well, obviously, you know, it's not going to go through this. The power of this a, the power of compressing or stretching, it's stretched on the, it's stretched vertically. 0.4. Let's do 0.33333. 0.1, 0.001. Oh, almost looks like a line. Okay, it's fine. Okay, so that's it. Good job. Make sure you use Desmos graphing calculator. It's very good to, this is like an experimental station. We can dissect graphs, toy with them. What happens if I do this? What happens if I do that? Okay. 1 to 5, let me go over 5. Okay. And quadratic, these are zeros. Complex numbers, because they always come in pairs. Remember, it's a plus or minus bi. You could also have x plus or minus yi. This is the real number component. This is the imaginary component. To graph these imaginary numbers, we would move left or right 0 units. And then we will move up 4 units, put an open circle, move down -4 units, put another open circle. And whatever's going on, that's where those imaginary roots are. It's gonna be floating up above the axis because it's quadratic. So it's gonna have to be, it's gonna look something like that. Yeah. So let's start off with these imaginary roots. How do we address this? Well, it's 2 roots. So we say x equals 4i. When we set equal to 0, we have x minus 4i equals 0. X equals -4i. So we have x plus 4i equals 0. And those are the zeros. I'm going to FOIL this just so you see that when we multiply this out, those imaginary numbers definitely do disappear. They're sort of hidden, but they're still there. So we have x minus 4i times x plus 4i. So we have f o I l minus 4 squared is 16, I squared. This and this cancels out because they're opposites. So we have x squared minus 16 times, remember your iterations of I, the square root of -1 times the square root of -1 is just -1. So we're left with x squared plus 16. Hence x squared plus 16 equals this situation here. And again, just like I said in the previous video, we have the quadratic equation, it's lifted up 16 units. I'm going to stick with this, but this will work just as well. Actually, both of these will be good. Regarding my a, to make sure it goes through this coordinate, I will use this because it'll be easier using a with that than that. So we have, now we have to make sure it goes through this coordinate. We're going to use the ace up your sleeve method. Y equals a times x squared plus 16. The coordinate y is 10. X is -7. And again, we don't need to square this because the square is already here with this x squared. And we can't square this because they're different. This would be a complex solution. This is not a multiplicity situation. It's imaginary solutions, and imaginary numbers always come in pairs because of plus or minus. For those that maybe don't recall, the square root of 36 is plus or minus 6. The correct answer for the square root of 36 is +6 and also -6. If you have x squared equals 36 and you solve, you take the square root of both sides, x equals plus or minus 6. If you watch the deriving the quadratic equation video, that's where we get the plus or minus. That's why it's always 2 solutions, a positive and a negative version. So let's now go and solve for this a. 10 equals a times +49 plus 16 equals a times, it's late at night and I don't want to make mistakes, so yes, I'm using a calculator, don't judge me. But yes, shame on me. A times 65, 10 divided by 65 equals a. Even numbers, 5 goes into 10 2 times, 5 goes into 60. Jesus helps us all out and he loves us all. Yeah, I feel, okay. 5 times 6 is 30, 12, 13. Okay, 5 times 10 is 50, 10. Oh, shame on me. It's 13. Oh gosh. I said 13, but I wrote 12 down. That's why I constantly double check what I'm doing. Let me triple check. Remember, there's someone out there who could get a PhD, but they're like left a negative out or something like that. Okay. 2 out of 13 or 2 over 13, that's a perfectly valid number, some decimal. So our answer is, writing everything out for number 5, y equals 2 divided by 13 times, I'm going to go with the x squared plus 16. You can also write it as this. These are both perfectly valid answers. Let's go to Desmos graphing calculator. I will be graphing this because I don't know where I is in Desmos graphing calculator. Okay. Okay. I'm going to come back to Desmos graphing calculator. You see the little spinning wheel. I don't know why it's doing this. I need to probably update Microsoft. And this will probably be like this for the next 5 minutes. Therefore, I highly suggest graph this on your own and see where the solution is. Actually, you know what? Why bother? I tend to make things more difficult in my head for some reason. This is a simple, we jack it up 16 units. Like we're changing the tire on this. It's jacked up 16 units. The solutions, if that's 16, half of 16, +4, -4, open circle, open circle. Those are the imaginary solutions. Again, it's floating up above the x-axis. Imagine if you're walking down the street and you see someone floating in the air. Something's going on. Something imaginary, something that's not real. Hence, imaginary numbers are not real numbers. There's something else, something in the ethers, some whatever the heck ghost it is, whatever, however you want to describe it, the ghost of the number world. All this simply because we can't take the square root of negative numbers, so this is our workaround. Okay, so let's look at this cubit. Let's see, clear cut, clear cut. I'm going to leave 6 for you to do on your own for practice, and I'm going to do 7 because 7 involves the imaginary numbers. Again, I highly suggest you work this out on your own. At this point, we've dealt with imaginaries. Work it on your own and then maybe follow up with the video or something like that. This is easy enough, though. We got all these zeros, y-intercepts. Cubic. Cubic has 3 roots, 3 solutions, 1 real number solutions, 2 imaginary solutions. Y equals a times x minus 2 times x minus 3i times x plus 3i. There you go. There you go. I'm going to simplify this, and then I'm going to plug -1 in for my x and -15 in for my y. Get my little pad. Okay. Let me just work this out. In my head, I always say FOIL because I'm very absent-minded, and it helps remind me to keep track of everything. Okay, -9i squared, cancel, cancel, -9, -1, +9. So we have x minus 2 times x squared plus 9, a, y equals. So I'm going to plug in -1 for all of my x variables and -15 for my y variable. -1 minus 2, -1 squared plus 9. Okay. -15 equals a times -1 minus 2, that's -3. -1 squared is +1 plus 9, that's 10. -30, 15 over 30 equals a, 1/2 equals a. So the ace up our sleeves is a. You're gonna have to graph this on your own because relative to my Mozilla or whatever, Firefox, it's still, I don't know why it's stalling out, but it is. Graph this on your own. But our final equation in this case would be y equals 1/2 times, here we go, x minus 2 times x squared plus 1, plus 9. X squared plus 9. And that's the final equation. I'll sketch a quick something or another. We have a root at +2. Real numbered root, imaginary roots here. When we solve, our real part is 0. So we go up 3, we go down 3. There's no negative sign in front of the x value, so it's going to look something like this. So what I'm thinking, that has to be a +2. I'm going to graph this in my calculator next. Why am I doing that? Because we have a 0 at 2. As far as I know, there's no negative sign in front of. Did I leave a negative sign behind? That would be a negative sign, negative, or this would end up being positive, positive. I'm going to explore this further because I can't cross this x-axis here. That's the issue. Now, if I could do like this, that definitely will work, but I don't see a negative sign in front of any x values to tell me to flip it anyway, anyhow. So let me go ahead and graph this in my calculator because again, my Desmos, oh, hooray. The little thingy stopped spinning, so let's go to Desmos. I only do Desmos, it's a lot easier and it looks nicer. Y equals 0.5, parentheses, x minus 2, parentheses, x squared plus 16. Oh, sorry, x squared plus 9. 1/2 x minus 2, x squared plus 9. Let me turn this one off. Okay, so let's zoom out and see what's going on here. Oh, so there wasn't anything to flip it around based off the parent function x raised to the 3rd power. It does follow the same trajectory. It's just that it goes through the y-axis. I for some reason wanted to cross the left side. So it still has this root here. The imaginary roots are up here. I'm going to graph y equals 3 just so we can see generally where the imaginary roots generally might be. Y equals -3, y equals 3. Imaginary roots here, here. So it doesn't intersect at the imaginary roots, but you can see the influence imaginary roots have. They always either pull the function in its direction, or maybe it looks like it's repelling it away. Again, ghosts can't hurt you, but they can make you hurt yourself. That's something people say in horror movies or something. So you can see the influence of these imaginary numbers, even though they're actually not there. So it just came through here underneath and then came up. Okay, so I'm happier with that now. Okay, so it came up this way because the only way, because I was thinking if I came here, I would have to cross the x-axis, but I can't cross the x-axis. So that's what it did. So that's how powerful these roots are in terms of sketching things. Good job. And you see the importance of using Desmos in verifying visually what's going on. I'm going to go ahead and do this quartic for the heck of it. Quartic, so it's a degree 4. It looks something like this. And has 4 solutions. Bounce point at 2, so that means there's a multiplicity of 2 with this root. Other zeros, 1, 2, 3, 4. Y equals a times bounce point at 2, so it would have to be x minus 2. So when I solve, I get x equals 2. X plus 3, and x, I'm just going to throw an x in front, because anytime your root is 0, I'm not writing x minus 0 or x plus 0. I'm just throwing an x in there. So now we're going to use the ace up your sleeve method to figure out what a needs to be to force it through that coordinate. See, it's so simple, right? It's so simple. Okay, every x is 1. That makes things easier though. 1 minus 2 squared, 1 plus 3. Okay, so this is 1 times 1 is 1, 4. So what's that? Negative 4 equals a. So my equation here is y equals negative 4x times x minus 2 squared times x plus 3. Quadratic equation, 1, 2, 3, 4 roots. X to the first. This is to the first. Throw in your Mr. Sneaky 1 if it helps. Let's go ahead and graph this just to get in the habit. Negative 4x, x minus 2 squared, x plus 3. Quartic, that is something to note. Remember when I first did this, I said it will look something like that. However, our a ended up being negative. So that would flip it over. So instead of looking something like a w, it will look something like an m. That's the power of the negative sign in front. The rules still hold true. Share. And that's why it looks something like an m here. That's the y value. Okay, something like an m. Here we go. A root at negative 3, root at 0, root at 2. This would be your relative maximum. This would be your relative minimum. The end behavior as x approaches infinity, y is negative infinity. As x approaches negative infinity, y is also negative infinity. Hooray. On to page 22. Okay. Writing cubic. So now we're given the graphs, so I'm going to write cubic equations based on these graphs. Make sure to account for the given point here. It's some sort of cubic because in my mind I have an image of the parent function, except it looks like the parent function was reflected over the y-axis. So that means we're not multiplying everything by a negative number, but there's a negative sign in front of one of the x's, if not both of them, probably just one. Given points. So we know there's 3 roots. I have a root at 0, a root at x equals 4, and a root at x equals negative 5. So my equation so far is y equals a times x plus 5 times x. Let's throw it in parentheses so it doesn't feel left out. Times x minus 4. Definite, you see the importance of knowing your parent functions. Cubic, 1, 2 powers of 3 roots. So now, let's figure out what a is so we can make sure it goes to that coordinate. 5 plus 2. Okay. 2 minus 4 is negative 2. Negative 4, negative 28. So a is negative 1. So our equation is y equals negative 1 times something like that. So I'll graph this. I stand corrected. Well, technically, if I throw an x in front, but let's look at this and graph this just to verify. x plus 5, x minus 4. Yeah, I'm going to adjust these windows. It looks different only because it's different on the side, but it's the same stuff going on. Looks a bit more like what you have on your paper. 2 comma 28 when x is 2. Uh-oh, let's oh, okay, I'm crazy. 228. Okay, there it is. Hooray. Relative maximum, relative minimum, root, root, root. The end behavior as x approaches positive infinity, y approaches negative infinity. As x approaches negative infinity, y approaches positive infinity. That's the end behavior for this function. Hooray. Yeah. This is another quad or cubic function. You have your clear-cut roots, x equals 2, 5, 4, x equals -3. I think you're good with that. Practice that on your own. Oh, let's look at this one. This looks like a fun one. Let's jump and work on 10. Again, you have this, practice this on your own. The solutions will be posted. They tell us it's a quintic, so there's 5 solutions. Degree 5, a degree 5 function. If you graph the, like in the other practice, it's something like that. It just hugs the curve longer. It looks something like that. Starts here, ends here. It's something like that. It's just a bit more going on. The more roots you have spaced out, the more you have going on. Imagine if this was a roller coaster. That probably still won't work with all that physics. It's very, you have to be very careful to space out so there's enough relative to the momentum so you're not like going to go crash. It takes a lot of energy to then change directions like that. We have x equals 0, x equals 5. Oh, so we have a bounce point at 5. This definitely looks like a pass through, maybe of multiplicity 3. 3 plus 2 is definitely 5. Y equals a times x cubed times x minus 5 squared. There you go. Pass through, but it looks like a cubic function. If I zero in here, it looks like a cubic function here. So that's how we know it's not raised to the power of 1, but at least the power of 3. In order to be a bounce point, it has to be even. 3 plus 2 is 5. 128 equals a times 4 cubed times 4 minus 5 squared. 128 equals a times 64. -1 squared is +1. Those are related. 2. A equals 2. Y equals 2 times x cubed, x minus 5 squared. Voila, there you go. Isn't it wonderful? Looking at this, it's almost pretty much the same thing, except it's flipped. So something tells me our A is going to end up being negative for this one. Try this on your own and check your answers. That's all I can say. This looks like fun, so let's graph this for the heck of it. Okay. Okay, I'm gonna adjust it slightly for our graph. Yeah, That looks something like what we got there, right? Yeah. If this were a roller coaster and we wanted to space this out, let's make this 10. Oh no, shame on me, that made it worse. That's why it's good to do math beforehand so we don't have to make models. Oh, now it's like a kiddie roller. Well, except for this end piece. It's the kiddie roller, yay! And then we would have to get off here. That's like Jacob's ladder to heaven if we keep on going. Oh, let's flip this around. Let's see what happens. If I throw a negative here, let's move it up a little bit. Let's do +2. Do I dare? Okay. That was too much. So I don't know. We get on here on that raised platform. Yay! Duh, duh. And then we roll out. I would have to raise this power to make it. Let's flip it up though. Let's make this 4, 5, 6, 7. Looking at this. Oh, because I added it and moved it up. +30. Okay, I'm gonna be done with this, but this is really fun. I wanted to change this so it's skirted up. For those that are curious, please try this. Those of you that aren't curious, that's why I'm posting YouTube videos. You can do this thing called fast forward. You can speed through. This is your life, take it in your own hands. There you go. On to page 23. Okay, you have this, you can read through this. We've discussed the complex plane. The thing they call, instead of, they replace y with the imaginary axis, you'll even see a little I up here. Yeah, that's what it is. Remember, x plus or minus yi. This is the real number part, we move left or right. This is the imaginary number part, we move up and down. I'm going to go ahead and cover magnitudes here. I'm not going to include magnitudes on the test because I want to be done with this unit. For those of you that have physics, more power to you. A magnitude is nothing but the distance from the origin. It's the distance formula, people. It's really not that deep. Graph and label the following points. One thing we have to note, if this is 6, this is 2, 4, 6, 8. So always keep track of your units. Graph and label the following points. Again, you can pause and read this on your own. You'll be okay. Let me add parentheses here. They didn't come through. Let's graph Q. Imaginary points. I'm going to actually do open circles because they are imaginary. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, -12. Okay, so my real part, I'm going to move to the left 12. In my imaginary part, I'm going to go down 5. Let's go ahead and do this. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so -12, -5. -5 is halfway in between. -12, -5. We would put a little open circle here. That's the imaginary number. If we wanted to figure out the magnitude, if this were a vector and we wanted to figure out the magnitude from the origin, we could either use the Pythagorean theorem or the distance formula for this length. And that's the magnitude. It's not that deep. This is another imaginary number. Let's find S. In this case, there's a real number component, and there is no imaginary number component. So this isn't really imaginary. It's a real number. -10, that's a real number, so I'm going to put an actual closed dot there. The real number part here is 8. The imaginary part means I go up to +15. Now, granted, imaginary numbers do come in pairs. Down here with these quadratics, we will graph the pairs. This is just practice graphing singular imaginary numbers. But technically, this would be 8 plus 15i and 8 minus 15i. 10, 11, 12, 13, 14, 15, 16. I'll go ahead and post this for the heck of it. That would be the other part. And 6, 5. That would be the other twin, if you will, for this one. And that was R. Let's call this R prime, Q prime. This is S. S is real, so there's no need for that. T. The real number part is 0, so we don't move left or right at all. And we go down to -9, open circle. This is T. If you want its twin, T prime. There you go, it's so simple. Okay, I've already graphed quadratics in another video, but for those of you that don't bother watching the videos, maybe you should make the effort. I'll do like one of these, maybe 2 of these. Solve and graph each quadratic equation below, plus label the complex imaginary solutions. This is super easy. I'm going to do this one. I'm going to do C because C looks like it could be fun. This one, we could either complete the square or use a quadratic equation. Either way, it works out. Here we have x minus 5 equals plus or minus 7. Let me stop cutting corners. Plus or minus square root of -49, which would be x minus 5 equals plus or minus. The I comes out. I'm going to do this step by step just to make sure I don't make careless mistakes. Plus or minus 7i. Remember, if there's a negative sign in the square root, pluck out that negative sign, pluck out the I. So our solutions are x equals positive 5 plus or minus 7i. If this were a parent function, again, the graphs in your copy are fixed. This is my copy, I fix yours. We would move it 2, 3, 4, 5 units to the right. And remember the vertex, we have to set it equal to 0 to graph it in vertex form. And then we would move it up 49 units. That's a lot of units to be moving up, but it's going to be way up here someplace. The imaginary numbers, though, we can still do imaginary numbers. We move to the right 5, we move plus 7, and then we move down 7. And that's what that would look like. Let's graph this in Desmos just to see the influence of the imaginary numbers. Oh, for God's sakes. I'm going to have to come back because this thing here with the spinning wheel and all that stuff. Look this up for your own benefits. It's going to be up here someplace, and the imaginary numbers are down there. Notice there is a relationship between the 7 and that 49. Let me go ahead and graph this or solve this, and then maybe when I'm done, this little pinwheel thing will be done spinning. We have a solution here at positive 2. Solving this, x squared equals -9. X equals plus or minus square root of -9. X equals plus or minus 3i. So we have solutions 1, 2, 3 here. 1, 2, 3 here. I think we graphed something like this already. Only because we graphed this, let me go ahead and find the y-intercept. Remember, you can always find the y-intercept. What is y when x is 0? Y equals -2 times 9. So y equals -18. So it's some number way down here. It's cubic. So it's going to be something like bam, 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 whatever it is. And that's the cubic. There you go. I'm going to let you graph all that stuff on your own because my pinwheel's still going. For those of you that you shouldn't be uncomfortable using these. I'm going to go ahead and do B for those that are uncomfortable using the quadratic equation. We could complete the square, but why not use the quadratic equation? Let's look at B. 2a hang low, -b, plus or minus square root, b squared minus 4ac. A is 1, B is 6, C is 10. -6 plus or minus, that's a weird thing. 36 minus 4, A is 1, C is 10, so let's make that 40. 2 times A, oh, this isn't that bad. So we have -3 plus or minus something divided by 2, 36 minus 40, negative square root of -4, so we have 2i, plus or minus 2i. So x equals -3 plus or minus I. Let me triple check. Square root of 4 is 2i. 2 divided by 2. Okay. So whatever's going on with this quadratic equation, we move to the left 3. -1, 1, then we go up 1, down 1. Let me erase this because that's not a root. This whole function's moved up. And remember, changing b makes it a horseshoe pattern. I don't know where, oh, let's find the vertex. To find the vertex, remember it's -b over 2a. So it's -6 divided by 2, -3. Now I'm going to have to plug -3 into the actual equation to get the y value of the vertex. 9 minus 18 plus 10. 9 minus 8, 1. Oh, this is a little bit odd. Let me triple check this. I want to Desmos this out because I'm not happy with that getting a vertex smack dab at 1 because there's an imaginary number there. It shouldn't be there. Thankfully, the pinwheel stops. Okay. Let's just do the original one, x squared plus 6x plus 10. Let's change this. Oh, wow, okay. Well, that is where the vertex is. And it's saying it exists here. And when I plug in 3, I do get 1. I'm going to triple check my imaginary numbers to make sure they're where they should be. Let me do the, I didn't do the vertex one. Let me triple check. B squared, 36 minus 4 times 1 times 10 is 40. That's -4. -3 plus or minus square root of -4 over 2. -3 plus or minus 2i over 2. -3 plus or minus I. We move out -3. That's fascinating. Because it has imaginary solutions. It's just where the vertex is also where the imaginary solution is here. Plus there's one imaginary floating here. That's interesting. Like, I'm curious to see, generally speaking, let's say we're talking about trajectories. What's the difference between a trajectory where the imaginary number exists at the vertex versus one that exists away from the vertex? I'm just curious about that. Think about engineering and watch Hidden Figures and all that stuff. But I'm going to move on. This is it. Expect a one-question quiz, pages 21 to 23. Thank you. Have a wonderful night.